Now, in this particular example, we want to compare two different samples, and we assume that these samples are independently taken from each other and they are continuous. And we want to find out whether these two samples have been drawn from different populations or from the same population. Or in other words, is there a significant difference between the two sample means that we have here? And we can do that just simply by doing a simple t-test. And in Excel, there is a predefined function. So we start this function by typing an equal sign and then equals t, and we start typing and we come up with some options. And here you see, here you have this predefined function t-test that we are going to use. So we click on that and the program tells us what it actually expects us to enter. So the first parameter here is array number 1, and that refers to the data set for sample 1, separated by a comma. Then we have array number 2, and here that is the second array. And now it asks us whether we want it as a one-tailed or a two-tailed distribution. And just to remind you what this means, so a one-tailed distribution here means that we know that one of the sample means is larger than the other. So we can formulate it like that. A two-tailed test would be that we just simply say, well, we assume that they are different, but we don't know which one is larger and which one is smaller. So my advice would always be to go definitely for the two-tailed test unless you have very good reason to use a one-tailed test. So that is what we are going to do here. So we use a two-tailed test. And the last one is it asks us about the type of the test that we are going to do. And we have three different options here. We can give it a 1, 2, or 3. The 1 is the type when we have paired samples. Let me move that a little bit to that side. So when we have paired samples, when we have a before and after experiment, which we don't have in this case. Type 2 is a very rare case where this is the classical student t-test, where we have independent samples, where we assume that the variances of these two samples are exactly the same. Type 3 again is an independent test where our samples are drawn independently from each other, but it has unequal variance. And it turned out that for most purposes, it is this type 3 that gives the best and most accurate results. So I would always advise to go for type 3 unless you have a very good reason to go for type 2. If we are dealing with independent samples. So we put in 3 here, close the bracket, and we get a p-value. Let me write this down. P-value of 0.337, so 0.034. Now, what does that mean? We should have probably said in the first place that our null hypothesis would be that the two samples from which the two populations from which we draw our samples, that there is no difference. That would be our null hypothesis. And if we find a p-value that is smaller than our significance value alpha, and in this case we set alpha to 5%, so here alpha is 5%, or we can write it as 0.05, that's the same as 5%. In this case we can say H naught is rejected. Or, so if you remember, if P is lower than alpha. If P is low, H0 must go. So we reject the null hypothesis, and we say there is a difference between the two samples. So we know that the two samples are different, and what we need to do now is really, does this calculate or make a decision whether this effect really makes a difference? And to do that, we can calculate what is known as the Cohen's d. Let me write this down here. So Cohen's d effect size. Here's the equation for that, where we just simply take the difference between the two sample means, and I probably should say we don't care about the sign of the difference between the two sample means, divide them by the average of the two standard deviations. So obviously we need to calculate these things in order to see what Cohen's d in this case is. So what we can do is we can very simply calculate the average of the two samples. So again, in Excel, we have the pre-built function of average. So we start typing. So we calculate the mean for sample 1. Let's type, and then with left mouse button pressed, we get the numbers in there. So that would be the average for sample 1. And by just simply dragging it over to sample 2, we get the average for sample 2. So we see that both sample means are statistically significant different. So that was our means here. And we can calculate our standard deviation. And again, Excel has something predefined function. So, and you know that, of course, we just simply start typing standard deviation, and here we are standard def.s. That is for the sample standard deviation, and we just simply do the same thing that we've done for the average. So we just simply highlight the cells for which we want this sample standard deviation. And we get our sample standard deviation here, and by dragging it to that side, we do that for both samples. So what we can do now is we can calculate the mean difference. So here I just simply take this mean minus this mean. It doesn't matter which way around, because we said we don't care about the sign of that. So we get a mean difference of 9.33. Now we also need to calculate the average of our standard deviations. So what we do is we just simply calculate the average of our two standard deviations. That's this one here. So 5.97. And now for Cohen's d, what we need to do now is we just basically divide the difference. Oops, that actually should be a straight line, like that. So in this case, Cohen's d gives us, let's calculate that, equals 9.33 divided by 5.97, and this gives us a Cohen's d of 1.56. And if you remember from the list, Cohen's d larger than 1.2 is considered as huge effect. So what we see here is that the difference between the two samples is not only statistically significant, but in practice it's also considered as a really large and major effect. That is basically what Cohen's d tells us. Cohen's d calculation, of course, only makes sense if there is a statistically significant difference between the sample means.